Hello students and welcome to another video lecture from Architects Academy. Today's topic is going to be about RCC slabs. So the RCC slabs can be classified into two types, one-way slab and two-way slab. Let us see how we can define what is a one-way slab and what is a two-way slab. So when we are talking about a one-way slab, the first criteria is that the length to breadth ratio of the one-way slab is 2 or greater than 2. The second criteria is that the load which is acting on the slab is transferred in only one direction, and that is the reason why it is called as one-way slab. In case of two-way slab, the length to breadth ratio is less than 2, and the second criteria is that the load is transferred in both directions, and therefore it is called as a two-way slab. So let us now see this more in detail. So let us look at the diagram here, which is indicating a one-way slab and a two-way slab. So as per our definition which we talked about, we are seeing a slab here which has got a length of L here and breadth B. So when this length to breadth ratio is greater or equal to 2, we are going to call this as a one-way slab. Let us see the example. For example, in this case, let us say that L is 7 meters and the B is 3.5 meters. So the ratio of length to the breadth is 7 divided by 3.5, that is 2. Hence, as per our definition, we can say that this is a one-way slab. Let us look at the slab below. Here we are having the size of the slab as 6 meter by 4 meter. So if we take the length to breadth ratio, it is 6 by 4, that is 1.5 meter, which is going to be less than 2. So this will be called as a two-way slab. What you can see is that in case of the one-way slab, the load was getting transferred only in one direction. When a slab is bounded by such type of 4 columns and 4 beams, the load normally gets transferred along the shorter direction. In the second case, where this was a two-way slab, what you can see is that the load is getting transferred in both the longer direction as well as the shorter direction. So you will see that the way that the beams are designed also depends upon whether the load is transferred only in one direction or whether it is transferred along both the directions. Now let us look at the one-way slab in detail. In this particular lecture, we are going to only focus on one-way slab. We are going to learn about two-way slab in the next lecture. So I've got a sketch here of a one-way slab, a drawing. So the slab consists of a length of 7 meters by 3.5 meters. It is bounded on the 4 sides by columns C1, C2, C3 and C4. And the slab has got beams B1, B2, B3 and B4. Since the ratio of the length to the breadth is 2, 7 divided by 3.5 is 2, this slab is going to be a one-way slab. So what we'll see is that the load is going to get transferred along the shorter span here. So since the load is getting transferred along the shorter span, the main reinforcement is also going to run along the shorter span. As you can see here in the red color, what you are seeing is the main reinforcement in this slab. The main reinforcement, as you can see, has got a bar which is bent up near the support. So it consists of alternate bent up bars which are bent up at 45 degrees at a distance of L by 4 from the face of the beam. Why these bars are bent up at 45 degrees? We'll see that reason slightly later on. At right angles to this main reinforcement, what you can see in the blue color is the distribution steel. Now, what is the reason for providing the distribution steel also we'll see further in the lecture. All the bars in this slab are not shown. So this is just a representative area of the slab which has been shown. In actual reality, the entire slab will have the bars which are covering the entire slab. What is the distance between these bars or the diameter of these bars is governed by the load conditions and the calculations done by the structural engineer, and therefore we need not worry too much about the center to center distance between the bars or the diameter of the bars. We can say that as a general rule, the center to center distance between bars will vary between 110 mm to about 175 mm depending upon the loading conditions. Now further on, what we will see is that if we look at the section of this slab, if we take a section through this slab, for example here we have taken a section AA through this slab, what are we going to see in the section? So if we look at this particular section, what we are going to see is that the section is going to get cut through these two beams B2 and B1, and it is going to get cut through the slab. So on the left hand side here, we are going to see this beam B2. So I'll just indicate this beam B2 here. And on the right hand side, we are going to see this beam B1, which is going to be on the right hand side. So B1, B2 and B1. And in the center, what we can see is the slab. Now if we look at the slab more in detail, what you will see is that the main reinforcement which has been shown in the red color, that is placed with alternate bars bent up as has been shown here. As you can see that this bar has been bent up here, and then there is the bar beyond that which is shown in the dashed lines. So as you can see, this bar is shown in the dashed line which is beyond this bar, which is shown like this. So what you will see in the plan is this bar which is seen here, while as the bar which is behind it or beyond it is the bar which we are seeing here, and therefore it is being seen dashed because it is beyond this bar. Now the distribution steel is being seen as these blue dots which are at right angles to the main reinforcement. You will also see that this particular main reinforcement is bent up at a distance of L/4 from the beam. The reason for having this bent up bar we'll see slightly later. But as you can see, this bar now gets bent up and the main reinforcement now goes at the top layer of the slab, and therefore now the distribution steel also is going to be here seen. What you will observe is that in this particular case, that is at the bottom of the slab, the distribution steel is above the main reinforcement, but at the top of the slab, what you will see is that the distribution steel is below the main reinforcement. So remember this important thing, that location of distribution steel, how it is. Now another important thing that you should note is that this particular main reinforcement also gets anchored inside the beam like this. This is very essential because when the slab bends, the tendency of the steel is also to bend along with the slab, and it will get pulled out from the beam if there is no sufficient anchorage of the steel inside the concrete. So this length up to which this bar is going to get embedded inside the beam is going to be called as the development length. We'll talk about development length more in a further video. if you look at the reinforcement inside the beams now, you will see that the beams have some typical reinforcement, two bars at the top which are called as the anchor bars. Then there are these main reinforcement bars which could be 2 to 3 bars or 2 or more bars at the bottom, which are the main reinforcement in the beam. And these are going to be tied with these types of rings, reinforcement bar rings, which are called as the stirrups. We'll learn more about the beam reinforcement in another video. So I hope this section is clear to you. Another important thing which you should note is that this bar is bent up at an angle of 45 degrees. Why this is 45 degrees again is another point of discussion which we will cover later. Now why does this steel move from the lower fiber of the slab to the upper fiber of the slab, and why there is going to be this bent up bar? These two reasons are to do with the way or the behavior of the slab when it is subjected to load. So that has been shown in these sketches here. So as you can see, when the slab is acted upon by a UDL, what will happen is that the slab will have a tendency to sag. When this sagging occurs, the beams, since they are cast homogeneously along with the slab, will resist this sagging at the junction, and therefore there will be some amount of hogging which will occur at the near the beams. So as a result of that, what you will see is that near the beam there will be hogging, while as in the center of the slab there is going to be sagging. So because of the hogging which is occurring near the support, there will be tension created at the top, while as due to sagging which is occurring in the middle of the support, there will be tension created at the bottom. So you know that wherever there is tension inside the RCC slab, we require to provide the reinforcement, because concrete is not good in taking the tensile force. So this is the reason why you will see that at the point where this type of tension gets created, we require to have this additional steel at the top, which is going to resist the bending or the negative bending moment as we call it. This can be seen also with the help of a bending moment diagram, which you can see here. So the maximum bending moment will be at the center, which is seen here. It is a positive bending moment, therefore it is above the baseline. And here you are going to have the negative bending moment, which is seen here as indicated by negative BM here. So as a result of that, we are going to require to have the steel here and this portion and in this portion in the slab. Another reason for having this bent up bar is that the slab is also going to develop shear as a result of the loads. So you are aware about what is meant by shear force diagram. So if you look at the shear force diagram caused due to the UDL, what you will see is that the maximum shear acts somewhere near the beam, and therefore we require to resist that shear. So another reason why this bar is bent up here at 45 degrees is that it will also help in resisting the shear which is being caused in this zone, which you can see here. So these are the two important reasons why the bent up bars are provided, and I think that should be clear from this these sketches which are showing the sagging and hogging in the slab, the bending moment diagram and the shear force diagram in the slab. So let us look at these reasons more in detail. This will be part of your exam paper, and therefore you can take this down. Reasons for bent up bar in the slab. So these are the reasons are twofold. One is that the reinforcement near the support changes location from the lower part of the slab to upper part of the slab as per the change in the tension zone as shown in the diagram which we saw. Then the second reason is that the bent up bar also resists the shear stresses near the support. Again, here we can refer to the shear force diagram which we talked about here. And so these are the two important reasons why the bent up bars are provided in the slab. Another important point which we have to discuss as far as the slab reinforcement is concerned is the purpose of the distribution steel, which we have not seen earlier. So you know that the distribution steel is provided at right angles to the main steel. So what is the purpose of the distribution steel? So what you can see is that the distribution bars are tied to the main reinforcement by means of binding wire. As a result of that, they form a sort of a mesh, a two-way mesh with the main reinforcement and the distribution steel at right angles to that. This helps in various ways, which we will now talk about. So the first thing is that the distribution steel distributes the load from the main reinforcement throughout the slab. The second reason is that the distribution steel ties the main reinforcement and prevents the displacement of the bars during the construction work. So during the construction work, there are going to be a lot of movements on the slab of workmen and equipment and other things. So there is always a possibility that the reinforcement will get displaced. Since the main reinforcement is tied to the distribution steel by binding wire, it will ensure that such a displacement does not take place. The third reason is that because this main reinforcement is tied to the distribution steel, the main reinforcement it ties the main reinforcement and prevents or maintains the distance between the main reinforcement bars. So this is very important. The main reinforcement, I think you can get rid of this. So it ties the main reinforcement and maintains the distance between the main reinforcement bars. So this is the third reason. So what you can see is that these are the three important reasons why the distribution steel is provided in case of the one-way slab. So I hope this was clear to you what is meant by one-way slab, what are the different reasons for providing distribution steel and bent up bars, and I hope you will be able to draw the drawing in the exam. In the exam you will normally be given just the size of the room. It will be not mentioned whether the slab is a one-way or two-way slab, so you will have to work that out based on the ratio of length to breadth as we talked about. And then you will have to draw this sketch, rather this plan to a scale showing the main reinforcement and the distribution reinforcement, and a section through that which will again show the main reinforcement, the distribution steel, and also the reinforcement inside the beam. So I hope this is clear to you. We'll see more about two-way slabs in the next video. Thank you.